Okay, so now we'll move to a little bit of math here. So we just try to use a very simple mathematics to derive this Petty approximation, just to make sure that we understand the principle properly. So where does this come from? I mean, yeah, so okay, we know that we're gonna use this, but where does it come from? So it's if you consider just the power series expansion, okay, so we know that the power series of e to the minus st is something like this, okay, over factorial 2 and minus st cube over factorial 3 and so on and so forth. Okay, so this is how the power series expansion looks like. So what we want to do is we want actually a rational function that tries to approximate this power series. The advantage of using a rational function is that okay, this is a first order rational function, so we have first order numerator and first order denominator. So it's only from a control perspective, it's just adding 1, 0, and 1 pole to the system. But also on the other hand, it can be used to approximate the system which is higher than first order. So if we use just this 1 minus st, which is the first order approximation of e to the minus st, it's not going to be as accurate as this one, as we will see. So so how will we proceed here? So it just comes from the power series expansion, so of first order rational function. So if you have a general rational function which looks like this, okay, and divided by d1 s, so this is the numerator and denominator, okay, so it can be shown that this is the like the expansion or the power series expansion of this rational function. So it looks something like this, okay, divided by d node squared multiplied by s, and then you have another term here, d1 squared n node over d node cube minus d1 and 1 over d node squared multiplied by s squared and so on. So all we need to do here is just to equate the terms. So we just say that, okay, n node over d node is equal to 1, and then this term here is going to be equal to negative t, right? And then this term over here will be equal to t squared over factorial 2. So if we equate those three terms with those three expressions, so we can solve for n node, d node, n1 and d1, okay? And from this first expression, for example, we know that n node equals to d node, because n node over d node equals 1, and then we start substituting in those other terms, and eventually if you set, because you have like a higher, you have more unknowns than you have equations, so you can just set n node equals d node equals to 1 without loss of generality, and then you can just substitute with those terms, and eventually you will get the following. What you will find is that d1 will be equal to d node times t over 2, which is basically t over 2, and n1 will be equal to minus t over 2. Okay, so if you then substitute in this expression, so you will then find that, okay, then the e to the minus st will eventually be approximately equal to n1, which is negative t over 2, okay, times s plus 1 divided by t over 2 times s plus 1. And this is what we call the Petty approximation, okay? So it's very simple. It just comes from the power series expansion of a rational function. And now if you expand this, so we know that it is correct. It provides a correct expansion of the e to the power st up to a second order degree. So which is why it's actually better than just the regular first order approximation. And this is an advantage that we get from this rational function approximation. So yeah, okay. So if we now that we have derived the expression for the Paddy approximation, so we just want to now summarize this control design method again. So as we said, the process goes as follows. So you have, this is your controller that you want to design, and then we have our zero order hold, okay, which is, as we said, it's 1 over s minus 1 over s e to the minus st, and we obtain this e to the minus st from the Paddy approximation. Okay, so we obtain the e to the minus st from the Paddy approximation, and then we have a transfer function for the zero order hold, and we also have our transfer function for our system and for our sensor. So now we can safely start to design our controller. So first we start with a continuous model for the G and H, as we already did in the previous continuous time control design. Then we add a zero order hold block based on the Paddy approximation, because it's a rational function that we can easily integrate into our linear control system theory. And now that you have the zero order hold transfer function as well, you can then start to design your continuous time controller. How will you design it? Whatever method you want. So you can use all the different techniques that we described in the previous lectures. You can start from a structure, for example, from a PID, and then you can use different methods. You can use root locus, you can use Bode plots, you can use whatever method you want in order to design your continuous time controller. And then what happens? So after you design your continuous time controller, so now you have the transfer function GC of S, which is your continuous time controller. You can use, for example, the bilinear transformation, okay, to obtain the Z domain transfer function, okay, the GC offset, because this is what we are eventually looking for, the discrete time version of the controller. And once we have the discrete time version of the controller, we can easily implement it. We can obtain its difference equation, and we can implement it digitally on a software or in hardware, as we explained in the previous lecture. Okay. So